Charges are arranged as shown in figure. The charges are arranged as shown in figure. This is minus Q. This is with 4Q. This is with minus Q. This is given x-axis. This is given x-axis. So this is x is equal to 0 point. X is equal to 0 point. So the distance between this and this is A. The distance between this and this is A. So the charges are arranged like this. Question is, calculate the electric field intensity. The electric field intensity. Calculate the electric field intensity everywhere on the axis. On the x-axis. So this is the question. So this type of problem is very important. We will see the solution to this problem. So how we can solve this problem. The solution to this problem is very simple. Suppose this is given axis. This is x is equal to 0. So this is minus q. This is A. This is another minus q. This is again A. So this region is x greater than A, and this region is x less than minus A, and this region is minus A less than x less than A. So if you calculate electric field intensity on these three regions, that is enough, because here they are asking calculate electric field intensity everywhere on the x-axis. So first of all, I am going for x greater than A. For x greater than A, what happens? So x greater than A means this is x is equal to 0 having 4q, x is equal to minus A having minus q, x is equal to A having q. So this region I am calculating. So the electric field intensity is nothing but, first of all, place a unit charge. Place a unit charge. Place a unit charge on x greater than A region. On x greater than A region, and calculate force on this unit charge because of remaining three charges. That is, force on this due to Q. Force on this due to 4Q. Force on this due to minus Q. That is F1, this is F2, this is F3. So we are having three forces. So if we calculate forces on the unit charge because of three charges, that is nothing but electric field intensity. Because I am placing unit charge there. Wherever you want electric field intensity, just keep a unit charge and calculate force on that unit charge because of remaining charges. So that is enough. So here I am calculating forces, three forces like this. So if you calculate, the total electric field intensity is because of F1 plus F2 plus F3. So what is F1? Force on unit charge due to Q. Force on unit charge due to Q. So that is given by Q by 4 pi epsilon naught What about distance? Distance, here I am assuming this is x greater than x is equal to a. So this is, here I placed unit charge. So this is some starting from this is I am taking some x. Sorry, this is x is equal to a. This is x is equal to 0. This is x is equal to minus a. So starting from x is equal to 0, consider the charge, unit charge is located at x. So this is reference point. So always the unit charge is from reference point. So at a distance of x, So what is this? This is here q charge. This is 4q. This is minus q charge. So what is this distance? This is a. This is a, and again this is a. So this is x minus a. This is x minus a. So this is x. What is this total distance? This is x plus a whole square. So the force on unit charge due to q is q by 4 pi epsilon naught into 1 by r square, distance x minus a whole square. And along here this is x axis. So this is ax bar. Plus force on unit charge due to 4q by 4 pi epsilon x square ax cap minus y minus means because of third minus q by 4 pi epsilon naught x plus a whole square ax cap. Therefore E is equal to take ax cap common and q by 4 pi epsilon also common, q by 4 pi epsilon common, 1 by x minus a whole square plus 4 by x square minus 1 by x plus a whole square ax bar. So this is the electric field intensity at x greater than a. This is for x greater than a at any point. Suppose some x value is given. Directly if you substitute that x value, directly you can calculate the electric field intensity. A very interesting problem. Similarly, second case for x less than minus a. Because here if you observe in the axis, this is x is equal to 0, 4q is located, this is q, this is minus q. So this is x greater than a, this is x less than minus a, this is x greater than a. Since it is exactly opposite to here along x-axis, normal to x-axis, it is maintaining symmetry. Therefore, we can say that suppose this is E1, E2 electric field for regions less than minus a is exactly opposite to E1. That is E2 is equal to, directly we can say that minus E1 because of symmetry. Now for minus a less than x less than a, so this is the region we have to consider. So this is x is equal to 0, minus a. First of all I am calculating in this region, that is minus a less than, the region is 0 less than x less than a. Then what happens? So in this region keep a unit charge. So the unit charge, this is the unit charge. So this is here I am having q, here I am having 4q, here I am having q. So force on this due to q, like this, in this direction. Force on this due to 4q, like this. Force on this due to minus q, like this. So total electric field intensity, suppose this is E3 is equal to force on unit charge due to Q, that is given by, so now this from x is equal to 0, the distance is x. The distance is x. Now what is this? Total one is A. This is A. So this is now A minus x. So the E3 is equal to Q by 4 pi epsilon naught A minus x whole square. What is the vector direction? Since the force is in this direction, the force is this is x. The force is in minus x direction. The force on this due to Q is minus x direction. So minus ax plus force on unit charge due to 4q. 4q by 4 pi epsilon naught x square ax cap, positive direction only. Similarly minus q by 4 pi epsilon naught. What is the distance? So this is a x plus a whole square, ax cap only. So if you take ax common, q by 4 pi epsilon naught also common. So this is minus 1 by a minus x whole square plus 4 by 4 pi epsilon, plus 4 by x square minus 1 by x plus a whole square ax cap. So this is the answer. Similarly, if you go for minus a less than x less than 0, E4, because of symmetry, E4 is equal to minus E3. E4 is equal to minus E3. So here this point is very interesting. Why I am taking minus ax? This minus ax is because like this. Because this is the Q, unit charge is below Q. That's why the force is in opposite direction. We have to consider in minus x direction. That's why I am writing here minus x. So if a particular value of x is given, directly you can substitute and you can calculate the electric field intensity. So this is a very, very interesting problem. Next problem is, it is required to hold 4 equal point charges of q coulomb each in equilibrium at the corners of a square. What point charge to be kept at the center of the square, so that the charges would be equilibrium. The charges would be equilibrium. In the bracket, equilibrium means the resultant force acting on any one charge which are the resultant force on any one charge which are located at the corners of square is 0. That is, the resultant force on any one charge is 0. Then equilibrium is maintained. So the question is, what point charge to be kept at the center of the square to maintain equilibrium? So the solution to this problem, I am just giving a hint how to solve this problem. Here it is given like this. A square is given. This is X. This is Y. This is a 4 point charges of Q coulomb. So this is a Q coulomb, this is a Q coulomb, this is also Q coulomb, this is also Q coulomb. So this is located at 0, 0. Suppose the equilibrium corners of a square. Suppose this is a square A, 0. That is the length of side is A, 0. Then this is located at A, A. Then this is located at 0, A. Then what is the point charge to be kept at the center of the square? So I have to keep at the center of the square such that equilibrium is maintained. That is, equilibrium means the resultant force acting on any one charge which are located at the corners of square is 0. So I am keeping a charge. Suppose this is the center of square. At the center I am keeping a charge Q1. I am keeping a charge Q1, which is a fifth charge. So to maintain equilibrium, the resultant force acting on any one charge which are located at the corners must be 0. That is, suppose if I consider this, the force acting on charge 1, due to remaining 4 charges must be 0. The resultant force must be 0. That is, the force on Q due to 2 is like this, in this direction, F21. Similarly, the force on Q due to 5 is F31. The distance is only this part. For that. This is F51. The force on Q due to 3 is in this direction. The total distance is this one. You have to calculate what is the distance. Okay, because this is a square, so this is A, this is also A. So the diagonal is square root of A square plus A square. So A square plus A square means 2A square. So root 2A. So 1, 2, 3 is root 2A. So this is root 2A distance. This is half of that. This is half of the root 2A. That is root 2A by 2. This distance root 2A by 2. Right. So similarly, the force on Q due to fourth one is this one, like this, F41. So the resultant force, that is F21 plus F31 plus F41 plus F51 is equal to 0. So calculate the forces and make it 0. So here everything is very clear. Distance, everything is known clearly. So calculate all the forces and equate to 0. If you do like that, you will get the answer Q1, that is the point charge needed at the center of the square, is equal to minus 0.956 Q. That is approximately minus Q. Approximately Q1 is equal to minus Q. If you keep that one, so that equilibrium is maintained. So solve this problem and just verify your answer. The only thing is you have to calculate the forces acting on one due to because of the remaining 4 charges. That's all. You can solve this problem very easily. Next one is, we will see some electric field lines. Due to charges. This is for knowing purpose. Suppose a positive charge Q plus Q is located here. then the field lines are always away from the charge. The electric field lines are always away from the charge. So this makes a charge distribution. So the entire thing is field surrounding this Q is entire thing is having some field, some electric field E. So the field lines are always away from the positive charge. So this is a electric field of a positive point charge. Positive point charge. Similarly, if you consider a negative charge minus Q, the field lines are always into the negative point, so always inside. So the field lines are like this. The charge distribution, the field distribution is like this. The field is like this, electric field. So always the field lines are into the point. So this is E field of a negative point charge. E field of a negative point charge. Suppose if you consider positive charge and negative charge combinedly, that is the dipole. Suppose this is Q, this is minus Q, this is minus Q, so this is minus Q. Then how the field lines? One thing is, always the field lines are away from positive and towards negative. That is, the field lines leaves from positive and ends to minus Q. So starting from plus Q to minus Q. So like this the distribution. So like this. So the field distribution is like this. So leaving and towards negative. So the field distribution is like this. This is the electric field lines, E field due to a dipole, or E field due to a dipole. E field due to a combination of charges. You can say dipole. Dipole means two charges having equal magnitude but opposite sign. That is called dipole. So this is the electric field lines.